I want you to think for a second about, well, the device you are using to listen to this deep dive right now.
Which is probably, what, a smartphone?
Right, a smartphone or maybe a laptop.
Uh-huh.
And it's packed with millions of microscopic transistors running on this highly engineered lithium-ion battery. But consider what is actually processing the words you are hearing.
And it is definitely not the phone.
Exactly. It's the 3-pound mass of wet biological tissue sitting inside your skull. And, here's a mind-bending question to kick us off. When it comes to raw logic, to processing the underlying fabric of the universe, who is the ultimate mathematician?
That is the big question.
Right. Is it that 20-watt biocomputer inside your head, or is it, I don't know, a massive warehouse-sized supercomputer burning through megawatts of electricity?
I mean, it really is the ultimate computational battle of our time. We see headlines every single day about artificial intelligence beating grandmasters, generating incredible art, and, solving complex equations in milliseconds.
Yeah, it's everywhere.
It is. And it is very easy to look at that output and feel completely outgunned by the machines. To actually understand what is happening, though, we have to look under the hood of both systems.
Which is exactly what we're going to do today.
Right. We have to deconstruct the actual mathematics of how thinking works, biologically versus synthetically.
So we are pulling from some absolutely fascinating excerpts from an article titled The Mathematical Duel: Human Intuition versus Artificial Computation. We are going to deconstruct how artificial intelligence thinks compared to the human brain.
It's a great piece.
It really is. And most importantly, our mission here is to find out why sheer computational power hasn't made human intellect obsolete.
And we will break all of this down into fundamental mechanics. No advanced math degrees required, I promise.
Good, because I definitely don't have one.
Well, we are simply going to look at how a biological neural network fundamentally differs from an artificial one, starting with the sheer physics of it.
Okay, let's start with the power and efficiency paradox, because the contrast laid out here is staggering. The human brain contains roughly 86 billion neurons.
Give or take a few million. Yeah.
Right, and those neurons are forming trillions of synaptic connections. But the wild part is the entire operation runs on an average of just 20 watts of power.
It's crazy. To put that 20 watts into perspective, it is barely enough power to light up one of those dim little incandescent bulbs inside your refrigerator.
Wait, really? Just the fridge bulb?
Exactly. That is your daily power budget for consciousness.
That is insane. And with that dim little refrigerator bulb's worth of power, your brain is simultaneously processing high-definition stereoscopic vision. It is decoding complex language in real time.
Regulating your core temperature, beating your heart.
Yes, feeling emotions, and perhaps even doing some advanced calculus. All of it is happening concurrently. Then, you look at a cutting-edge AI model.
Right, and the contrast could not be more dramatic. When we talk about modern large language models or advanced neural networks, we aren't talking about a single machine sitting on a desk.
No, not at all.
We're talking about giant, sprawling data centers. I mean, training just one of these advanced models consumes megawatt hours of electricity.
Which is a massive amount of power.
It's the equivalent of the total power used by hundreds of households over the course of an entire year.
Yeah.
And that's just to train a single model to recognize patterns.
So how does biology manage to do with 20 watts what silicon needs a literal power plant to achieve? Like, what is the physical difference in how they are operating?
Well, it comes down to a fundamental architectural difference known as sparse activation.
Sparse activation.
Right. The human brain is ruthlessly efficient. When you are performing a specific task, say, trying to remember a childhood phone number or calculating a tip at a restaurant, your brain only fires the specific isolated neurons needed for that task.
So it's not using the whole brain at once.
Exactly. The rest of the network stays completely quiet. It conserves energy by only utilizing the pathways absolutely necessary for the problem at hand.
That makes sense. Imagine you are trying to find your keys in a massive 100-story skyscraper at night.
Okay, I like this.
What the human brain does with sparse activation is like walking into the building, turning on a single flashlight, and walking directly to the exact room you need. You shine a light, find the keys, and leave.
And the rest of the building stays dark.
Exactly. The rest of the building stays dark. Artificial intelligence, on the other hand, seems to walk into the lobby and slam a giant master switch that turns on every single light in every single room on all 100 floors all at once.
That analogy captures the energy waste perfectly.
Eh?
But to really grasp the mechanics, we have to look at how AI actually searches that skyscraper.
Okay.
AI networks rely on what we call dense matrix multiplication. So it isn't just turning on all the lights. Mathematically, when you ask an AI to find those keys, it is calculating the exact statistical probability of the keys being in every single drawer.
Oh, wow.
Yeah, of every single desk on all 100 floors simultaneously. It uses thousands of graphics processing units, or GPUs, to multiply massive, dense grids of numbers against other massive grids of numbers, just to spit out one single answer.
Which totally explains the megawatt hours. I mean, it's doing an astronomical amount of brute force math just to locate a single piece of information.
Exactly.
But if the human brain is so incredibly efficient with its tiny flashlight, what exactly is AI doing with all those calculations? What is happening in the bright lights of that metaphorical skyscraper?
Well, to understand the math, we have to recognize that AI does not understand concepts. It doesn't know what an apple is,
Yeah.
it doesn't know what a car is or what sadness is. At its very core, the universe of AI is built entirely on pure, unadulterated linear algebra and multivariable calculus. It only understands numbers.
Okay, let's unpack this because this is where the article gets incredibly dense. If an AI doesn't know what an apple is, how is it writing beautiful poems about apple orchards? I mean, how does a word become a math problem?
Through a process called vectorization. In the AI world, every single word you type, every image you upload, every idea you try to communicate, it all gets mathematically converted into a vector.
A vector.
Right. A vector is essentially a giant list of coordinates. Imagine a map, but instead of just north, south, east, and west, this map has 10,000 different directions.
10,000 dimensions. My brain hurts just trying to picture that.
Right. It's impossible for us to visualize. But every word is assigned a specific coordinate on that 10,000 dimensional map based on how frequently it appears next to other words in human literature.
So it's charting the distance between concepts. Like the vector for dog would be mathematically closer to the vector for wolf than it would be to, say, the vector for poster.
Yes, that captures the mechanism perfectly.
Mhm.
And it gets even more fascinating when you apply multivariable calculus to those coordinates.
Because they're just numbers.
Exactly. Because these are just numbers, you can do arithmetic with concepts. The classic example in computer science is taking the vector for king, mathematically subtracting the vector for man, and adding the vector for woman.
And what does that give you?
The resulting coordinates will place you almost exactly on the vector for queen.
Oh, wow. So it isn't reasoning about royalty or gender at all.
Not at all.
It is literally just adding and subtracting coordinates in a high-dimensional space.
It is multiplying those massive matrices of vectors. When you feed a sentence into an AI, it translates your words into those thousands of numbers, multiplies them against billions of other numbers in its neural network, and uses calculus to calculate the probability of what the next number should be.
So it's constantly predicting the next logical step.
Exactly.
I have to challenge this premise, though. If an AI is literally just calculating probabilities to predict the next logical coordinate in a sequence, is its intelligence just an illusion?
That is the big debate.
I mean, it sounds like we are basically just looking at a mathematically flawless, super-powered autocomplete. Does it actually know anything, or is it just mimicking understanding by guessing the next word really, really well?
What's fascinating here is that you are highlighting the biggest philosophical divide in modern computer science.
Really?
Oh, absolutely. In a strictly mechanical sense, yes, it is predicting the next step based on probabilities. But we cannot dismiss it as merely an illusion because the sheer scale of this brute force math creates something entirely new.
Oh, so?
We are talking about systems that process petabytes of data. They scan millions of documents and find hidden, multidimensional statistical correlations that a human being could never notice in 100 lifetimes.
So you are saying the line between guessing based on statistics and genuine problem solving gets blurry when the machine has read the entire internet.
Think about the depth of those calculations. When a machine is executing billions of multivariable equations per second, predicting the next logical step requires mapping the underlying logic of the universe.
That is wild.
If you give an AI a well-defined mathematical problem, something with clear rules and parameters, its speed and accuracy are practically infinite compared to us. It will calculate the probabilistic outcome flawlessly, mapping pathways through data that humans simply cannot visualize.
Okay, but that brings me to my next question. If AI is infinitely faster than us, if it is flawlessly accurate, and if it can process petabytes of data without breaking a sweat, why hasn't it completely replaced human mathematicians?
That is a very fair point.
Why do we still need biological brains doing math if silicon can map the universe so much faster?
The answer lies in the fundamental difference between calculation and comprehension.
Calculation versus comprehension.
Right. AI calculates. Humans comprehend. The text we are analyzing highlights three core advantages of the human mind that keep the 20-watt biocomputer relevant. The first advantage is semantic meaning.
The example from the article regarding semantic meaning is incredibly profound. Consider how a human child learns the number 1.
Oh, this is a great example.
Right. It's not just a digit on a page or some root memorization task. The child actually experiences the concept of unity. They hold one physical apple in their hand and feel its weight.
They interact with it physically.
Yeah. They look up and understand there is one moon in the sky. They realize they are one individual person. There is a deep conceptual reality to the number that is grounded in the physical universe.
Now contrast that with an artificial neural network. When an AI encounters the number 1, there is absolutely no reality attached to it.
Not at all.
No, it is entirely devoid of semantic meaning. To the AI, 1 is just a token value. It is a weight in a matrix, the mere dial turned to a specific position to help predict the next coordinate. The AI does not know what the number 1 actually feels like. It has no physical anchor.
It is like reading the chemical formula for water H2O versus the actual physical experience of jumping into a freezing cold swimming pool.
I love that.
The AI has the formula, but the human has the freezing water.
Exactly. And without that physical anchor, AI struggles to innovate outside its boundaries. Because humans have that semantic understanding, because we actually know what things mean, we possess the second major advantage, which is the ability to make abstract leaps.
Abstract leaps.
Right. Human mathematicians do not just calculate by brute force. They use spatial intuition. They use visual thinking.
The article specifically points to a branch of math called topology to explain this. For anyone unfamiliar, topology is the mathematics of shapes and spaces. It is the study of properties that are preserved through continuous deformations, like stretching or bending.
Right, and a classic topological example is that a coffee mug and a donut are mathematically the same shape.
Which sounds completely absurd at first.
It does, but it's true because they both have exactly one hole. You could theoretically mold a clay donut into a coffee mug without tearing the clay, just reshaping it. Humans can visualize this continuous deformation intuitively.
Here's where it gets really interesting. How does a mathematician use a donut to solve a complex equation?
By using that spatial intuition to build bridges between completely different fields of study, a human mathematician can look at a very messy, incredibly abstract, completely unsolved algebraic formula. And instead of just crunching the numbers, their brain can intuitively visualize the math as a shape. They might look at that messy algebra and intuitively say, the shape of this algebraic problem feels remarkably similar to the behavior of prime numbers over in this completely different discipline.
So they make a conceptual leap. They build a bridge between algebra and prime numbers based on an intuitive feeling about the geometry of the problem.
Exactly. And AI simply cannot make those creative nonlinear leaps. Remember, AI is calculating probabilities based on past data.
Right. It only knows what it has seen.
Yes. And AI can only find connections if those connections are already hidden somewhere in its training data. If the bridge between algebra and prime numbers hasn't already been built by a human and fed into the AI servers, the AI cannot intuitively jump across the gap. It is bounded by the limits of what has already been discovered.
And that intuitive leap ties directly into the third human advantage the article outlines, which is data efficiency. We established earlier that AI requires megawatt hours and petabytes of data to learn a concept.
Right.
But a human student operates completely differently. A student can look at 2 or 3 examples of a new geometric proof, just a handful of examples.
And I get it.
Yeah. Once that human brain grasps the underlying logic, they understand it forever. They have internalized the rule and can apply it to infinite new variations.
To achieve that same level of accuracy, an artificial neural network might require 10,000 variations of that exact same geometric proof fed into its system.
10,000.
Easily. The AI has to mathematically map every possible permutation to statistically guarantee it gets the right answer the next time.
Think about teaching someone to play chess. If I sit down with you, I can explain the rules of chess in maybe 3 games. I tell you how the knight moves in an L shape, how the bishop moves diagonally, and that the goal is to trap the king.
Right, and I understand the parameters.
You comprehend those rules and immediately start forming strategies. You might play terribly at first, but you know how to play. An AI does not comprehend the rules of chess.
Not at all.
To learn the game, an AI has to process 10,000 previous chess matches just to mathematically guess what a good next move looks like based on the statistical probability of past winning moves.
It's an incredibly inefficient way to learn if you don't actually comprehend the mechanics of the game. If we connect this to the bigger picture, you can see why human mathematicians are absolutely vital.
Yeah, that makes a lot of sense.
Without organic comprehension, without those topological leaps and that intuitive grasp of semantic meaning, mathematics would stagnate. AI can calculate the permutations of known rules faster than anything in the universe, but it requires the human mind to intuitively discover the new rules.
It is a completely different paradigm of intelligence. The conclusion of the analysis focuses heavily on synergy.
Yes, synergy is the key word here.
We are so conditioned by science fiction to view this as a zero-sum game of humans versus machines, a battle of who replaces whom. But this deep dive reveals that they are simply two entirely different mathematical philosophies.
They are complementary tools, not strictly adversarial forces. Artificial intelligence is the ultimate calculator. It is a hyper-fast, multidimensional matrix machine that can process the known universe of data in milliseconds. It provides the brute force.
And the human brain is the ultimate architect. We are astoundingly energy efficient. Our thinking is driven by deep conceptual meaning, and we possess the spatial intuition required to make nonlinear leaps of logic.
Exactly. The future of mathematics, and frankly the future of complex problem solving in any discipline, doesn't belong to artificial intelligence operating in a vacuum.
No.
And it certainly doesn't belong to humans stubbornly working without these massive computational tools. The most profound discoveries of the next century will belong to the humans who learn how to guide the immense computational power of AI with their own organic intuition.
So what does this all mean for you, listening to this right now? It means you shouldn't feel threatened by the rise of AI.
Absolutely not.
You shouldn't let the sheer volume of information these machines can process make you feel obsolete. In this new technological era, your job is not to compute faster than a machine. You will never win that race, and you certainly don't have the megawatt power supply to try.
Leave the computing to the machines.
Right. Your job is to be the organic architect. Your job is to understand what things actually mean, to make those intuitive leaps across different disciplines, and to point the AI's massive synthetic power in the right direction. You provide the compass, the machine provides the engine.
That is beautifully put, and it actually raises an important question for the future of hardware itself. We've established that the 20-watt human brain uses sparse activation, making it the absolute pinnacle of energy efficiency precisely because it relies on organic biology.
Right, the flashlight in the skyscraper.
Yeah. Exactly. As AI models continue to scale up, their massive data centers and megawatt energy demands are becoming increasingly unsustainable. Will the future of artificial intelligence eventually force us to abandon silicon chips entirely?
Oh, wow.
To solve the AI energy crisis, might the supercomputers of tomorrow be grown in a lab from living biological tissue? It leaves you wondering if the ultimate future of artificial computation isn't synthetic at all, but rather a return to the organic.
That is a staggering possibility to consider. The ultimate universe mapping machine might just end up looking a whole lot like that 20-watt biocomputer already sitting right inside your skull.